Hey there again. I keep saying this will be a quick video, and I think this time I will live up to that. We're going back to the physics problems, and I was debating skipping this chapter. It's on simple vector manipulation, but for the sake of completeness, I will do it, and it will amount to basically just using Python as a calculator. But occasionally, I have had had the opportunity or the need to use some of the vector manipulation functions like dot product or cross product in real work. So while it might be a little bit on the simple side, we will be doing a couple more complicated videos right after this, some in the physics field and some in the finance field. So I figured a simple one beforehand would be a good idea. So with that being said, let's get going. So let's zoom in here. Is that a little big? We'll shrink it if the need arises. So the problem is really simple. A man flies from Washington, D.C. to Manila, and we are asked to calculate the magnitude of the displacement vectors given the latitude and longitude coordinates of both cities. So obviously this is a really simple problem. It can easily be done by hand, but we're going to use NumPy's vector manipulation abilities to do it. So here's a two-dimensional schematic representation of what's going on. I was too lazy to actually draw this in 3 dimensions, but we have two vectors going from the center of the Earth, one to Washington, D.C., and one to Manila. And then we're asked to calculate the magnitude of this line that's drawn here in red. So again, it amounts to a simple geometry problem in 3 dimensions. So procedurally, this is what we're going to do. We're going to transform those longitude and latitude things to more kind of standardized spherical coordinates and then change those into Cartesian coordinates. And from there we will just use NumPy's basic vector arithmetic and the norm function to actually get the results. So transformations from spherical coordinates to Cartesians are pretty simple. They're given by these equations here. This is how we're going to set up our coordinate system, and we're going to take the XY plane as slicing the Earth through the equator. So if we go to a map of the Earth, this would just basically pass through the equator here and divide the Earth into northern and southern hemispheres. Likewise, we will take, where is my thing here? Okay, we will take the XZ plane to cut through the prime meridian, basically cutting the Earth into eastern and western hemispheres. So that's how we're going to set up our coordinate system. And so let's actually code this up. We're just going to need NumPy for this, nothing fancy. I'm going to import the sine and cosine functions explicitly because we use them a bunch to implement these equations here. And I've already entered in the radius of the Earth in kilometers. And we're just going to take the Earth to be a perfect sphere rather than a spheroid. So I'm going to put in the coordinates of Washington, D.C. and the coordinates of Manila as well. Okay, now that that's done, we're going to build our coordinate system here. So let's create a variable called theta underscore DC, and that's going to be the longitude coordinate of DC converted into spherical coordinates, and that's just going to be 360 degrees minus, what is our position, 77 west. So that's our theta variable. Likewise, phi underscore DC is going to be 90 degrees minus 39 north, 39. So we could do the same thing for Manila. So let's go down here. Let's create a variable called theta underscore m. And that's going to be equal to, in this case, it's just going to be equal to 121 east. Phi underscore m is going to be 90 minus 15. Okay, and for bookkeeping purposes, I would like to keep things kind of together in their own vectors. So what I'm going to do is create a vector of spherical coordinates. So I'm going to create a vector called DC spherical, and just enter in the spherical coordinates in the form. The first component is going to be the radius, the radial component. The second component is going to be theta, and the third phi. So let's do that. So let's see. I'm just going to copy and paste here from my test code, and I'm going to do the conversions from degrees into radians here. So like I just said, this is the radial component, this is the theta component, and the phi component, and we're using a built-in function, np radians, to convert degrees into radians. So we're going to create another variable called DC Cartesian. We'll just call it DC underscore cart, where this is these converted into Cartesian coordinates. So for the first component, it's just this. This is essentially this r sine phi cosine theta. So there's our r, the zeroth component. The sine phi, that's the second component here, the last component of that vector, and cos theta. And likewise for the next two, I'm just going to again copy and paste this because it's kind of simple and straightforward. So that's the y and z components, and why are things all spaced funnily? Funnily, is that a word? Spaced funny here. Good enough. Let's just make sure this came in properly, and we'll do a print dc underscore cart. Okay, that looks like it came in properly, so we can get rid of the print statement, and we'll just do the same thing for Manila down here. So we'll do the same thing here. We'll create a spherical. We'll store the coordinates in its own vector, the spherical coordinates in its own vector, and then we'll just do the same type of conversion we did up here to go from spherical to Cartesian coordinates. So we'll do that, and let's just print this out again to make sure that it came in properly. M underscore cart for Manila Cartesian coordinates. Okay, that seems to work. So now we're just ready to actually answer the problem. So how do we do this? Well, it's just the difference between these two vectors. So if we ended at Manila and started at DC, we could just take the Manila vector, subtract the DC vector, and that gives us this vector here. And then we just take the norm of that, basically the length of that vector, and that's our answer. So let's create a vector called D, and that is going to be equal to M cart minus DC cart. And let's print displacement is equal to the norm of that vector D. So that's NP. I think it's in lin alg, and then D. So let's see here. Oops, what did I do? Oh, I forgot to put in the norm function. It's linalg.norm. So there we go. There's our answer. It's about 11,200 kilometers. So problem 2, a vector A lies in the yz plane, has an angle, makes an angle of 63 degrees with a positive y-axis, and has a positive z component. And it has a magnitude of 3.2 units. Similarly, we're given another vector B that lies in the xz plane, makes a 48 degree angle with a positive x-axis, and has a magnitude of 1.4 units. We're asked three things: find A dot B, A cross B, and the angle in between A and B. And I've reproduced the information here in the comments just so that we can reference it without scrolling back and forth. So let's go and get on with it. So let's build the vector now, and I guess I lied about scrolling back and forth, but if we have a vector in the yz plane here, and it makes an angle, let's call that angle alpha with a positive y-axis, then it has 0x component. That's pretty obvious. The y component is just going to be the magnitude of the vector times the cosine of the angle, and the z component obviously is the sine of the angle. So let's go down here, and we're going to put in our angle alpha is equal to, what was the angle again? It was 63 degrees. So alpha equals 63, and let's do np.radians 63. So our vector A is going to look like this. Again, it has 0 value in the x direction. It's its magnitude 3.2 times the cosine of alpha, and the z component is 3.2 times the sine of alpha. So let's go to the second vector now, B. So let's come down here and we'll create another angle beta, and that'll just be the 48 degrees expressed in radians, and our vector B is going to be equal to, let's see, B is just going to be this. Again, this lies in the xz plane, so it's going to have no y component, and it's just the magnitude times the cosine and sine of the respective angles for the cosine for the x, sine for the z, based on the information given. And now that's all we really need to do, and we're ready to actually answer the questions. So let's come down here and go print, let's say dot product equals, it equals np dot a comma b, and that should be just about it. Let me just run that to make sure there are no issues. And yes, that's exactly the number we're looking for, about 2.9. So likewise, I mean, we could even just copy this, insert it down here, and we'll just make this cross product. And likewise, NumPy has a built-in function called np.cross. That's that. And the angle in between, well, that's the dot product gives the dot product is basically defined as the magnitude of A times the magnitude of B times the cosine of the angle in between. So we just do a little bit of algebra, and we can come up with the answer easily. So let's print angle equals, now let's just go up here and actually do this. Angle is equal to, it's going to be np arc cosine, and it's going to be equal to the dot product divided by the product of the two magnitudes. So this is going to be np dot a comma b, and this is going to be divided by, what are our magnitudes here? 1.4. Where's my 1.4 times, and the other one is, what is it? 3.2. So what? Let's put a extra line in here. Put in the angle here. Run it, make sure there are no issues. So that should be the angle in radians, and let's convert it into degrees. So np dot rad, I think it's rad to deg for radians to degrees. What's the issue here? Looks like I need another parenthesis here. So yeah, there it is, about 48 degrees and change, 48.5 degrees. So the dot product just gives us back a number, the cross product gives back this vector, which we'd expect, and the angle, of course, is an angle. Cool. There's really not much to say here. Pretty straightforward. Next time, we're going to be doing a couple of physics problems. We're going to embellish it a little bit and do something a little more complicated, combining both differential equations and optimization problems. And on the financial end of things, we will be going back into looking at the probability of making 50% on certain types of option trades, more complicated trades and single options. We'll be doing spreads and strangles and things like that. So until next time, see ya.